Guys, it's again a pleasure to speak to you today. It's always reducing cost and learning how you can cut your cost and these massive cloud bills. It's something very, very dear to me. I suffered from it in my previous company where we had massive AWS bills that were very hard to understand. So I built the product that I wish I had at the time. Which is an automation on how to cut your cost and how to do it automatically, and then how to do it in real time, all the time, 24/7. So in this webinar, I'm going to show you first what's the pain and my personal frustration of this, as I share that pain with, I think, many people that are listening. And then I'm going to show it to you. So I'm going to take a cloud native application. It's Kubernetes. It's on Amazon. So I'm using EKS. And I'm going to run a tool that will automatically analyze my cost. Then it will, in the analysis of cost, it will tell me how much I spent, but it will also tell me how much I should really spend. And the difference between these two things is going to be your savings. And then I will show you how these AI techniques allows you to close the gap, meaning to reduce your spend to only what you should spend and nothing else, meaning nothing less, but also nothing more. All right, so let's do it. My name is Laurent. I'm one of the founder and I run product Forecast AI. Why are we talking about this? Why is reducing your costs such a difficult thing? And what's the frustration behind it? Well, the first one is, it is very hard on the cloud to use resources for what you should use them. And there's a lot of waste and over provisioning of it. In fact, there are two statistics. The first one is amazing. It's something from Datadog. This is actually something that Datadog is measuring for all of their Kubernetes customers, all their clients that are using Datadog with containers have these statistics that half of Kubernetes application use less than 30% of their CPU resource. It's exactly the same for memory. I think for memory it's 29%. But think about this. What that means is, if you take half of the world of Kubernetes, 1/3, so meaning, not 1/3, half of that world is over provision more than 3 times. If you turn this around, it means for half of the world, every month you are sending a check to Mr. Bezos of 3 times more that you really need to him for no reason, because you are not using these resources, but you are paying for them because they are sitting in your account. That's what this means. And the problem is massive, as you can imagine. There's another statistic from a research group that even goes further. She said that 90% of applications use 5 times more resources than they actually need. 5 times is all memory, CPU, network, and all the services that this application use. It's a generic statistic. The first one, though, is directly for Kubernetes containers from Datadog. So that's the frustration. It is very, very hard to use the resources that you need and to use only those and to not have any waste when you're thinking of cloud native applications. And that's actually an example. This is a real customer of ours. And we did this in January. So on the 20th of December, we onboarded that client. And you see this massive over provisioning. If you can't hear, so the blue line, the blue surface below is the amount of CPU that is necessary. The line above is the amount of CPU that was provisioned for this application. That's one cluster. It's a very large cluster. It's a cluster with 40 CPUs. They over provision 4 times. That's what it means. The difference between the blue line and the blue surface is 4x. And it's almost the same for memory. So you see how important and hard this is. And there is hope, but I will show you how to do this. We optimize them the 4th of January, and you see immediately a drop. And you start to see utilization and provisioning start to follow each other in a much better line. I will show it to you in a minute how this was done. But you see how massive that problem is. There is another thing. It's not your fault sometimes that these bills go out of control or sometimes even out of budget. It's not your fault because it's by design. And this is what our friends at the Hyper scaler at the cloud providers do a little bit. It's not just AWS, right? Google and Azure have the same idea. They don't help you. So they don't help you because their builds are complicated. They have a lot of choices. So AWS alone have hundreds of EC2 instances to choose from. Which one do you choose? They're very different. They have very different pricing. Which one do you take? And I took a screenshot of our AWS bill, and look at this. There are 33 pages on this bill. So what do you do with this? I mean, it's very long, it's complicated, it's hard to understand what they mean. I mean, look at this one. It says, I use zero, this one here, it's 1 cent because I use some data from Germany to Tokyo for 1 cent. I have 33 pages of that. And our total bill is hundreds of thousands of dollars. So you can imagine how, how hard it is to look at this, read this, and understand what it is that you need to do. For Kubernetes or for containers, it's even more difficult because as a developer, you have to answer several questions. And actually, some of these questions are not even answered by developers. They are different people in the development chain. The first question is, well, if you have a containerized application, 100 containers, how many machines do you need? It's called a node in the Kubernetes world. But that's the first question. It's very hard to answer. How many of these do I need to run my app? And you, as a developer or as a DevOps, you actually need to answer the question before you deploy. Then the other one, which is another of magnitude, is, well, now that I know how many, or that I decided how many machines I need, how many containers do I need? Like, how many replica of these things should I provision, and what should be the formula to add or delete a container, right? The reason why we all like Kubernetes is because you can scale very nicely, so you can add more containers easily for the same service, so you can scale very, very nicely as your application is growing in traffic. So the question is how many do you need, and what is the rule that you scale them? And once you know that, what should be the size of the container? So each container need to have a size. Do they use 100 millicore to the 0.1 core? Do they need 1 core? Do they need 10 cores? How much memory do they need? So you see, all these answers are interconnected together, interconnected. The answer of one question will impact the other two questions. This is why it's so hard to decide in advance how what's a real consumption of resources for my app. Now you start to understand, this is why the statistic of Datadog shows that in average, half of the world over provisions 3 times. It's very hard to do these things. It's very, very hard to do it, but there is hope. And this is what I'm going to show you. So the hope is the following. I have an application. I deployed it a few minutes ago. Actually, let me show it to you. Here, oops. Let me stop this. Just give me a moment. I need to stop my screen share. Here it is. So I deployed an application. It's on EKS. It's a containerized application using Kubernetes. EKS is the Kubernetes management platform of AWS. It's on Amazon. What you see on screen right now is an open source tool that allows the visualization of that application. So the application uses 6 machines. So they are called a node in the Kubernetes language. This is machine number 1, machine number 2, machine 3, 4, 5, and 6. Until all these purple rectangles are the machines, also called as a node or a VM. Inside each machine, you have containers. So the containers of these green rectangles have a bunch of application containers, as you can tell, into these boxes. The one above is my application. So all of this I'm showing to you, these are all my app. And the one below is the containers that Amazon need to run the cluster. So far, I did exactly like normal, like any developer would do. I deployed my applications on 6 machines. I didn't know how many I need, so I put 6. These machines are very standard. They're M5, so they're very popular for Amazon. And what I'll do now is I'm going to ask our AI engine, hey, how did they do this? Did I deploy this the right way? Did I select the right machines, the right number of machines? All of these questions are going to be answered by our AI engine. So to do this, I go to our product. This is our product. I go to add cluster. Here, I just connect the existing one. I don't need to create a new one. It's already there. It's already running. I have to connect, it's very simple. I'm installing an agent, very similar to how you would do for Datadog. So this is a small script that will install the agent. We have one version for Amazon EKS. We have one version for Google GKE, which is the Google Kubernetes Engine, or Kubernetes as a service for Google. We have the same for Azure, it's called AKS. And we have one open source version, KOPS, which in this case is for Amazon, but this is the open source version of Kubernetes orchestration platform. So in my case, it's EKS. What the very simple thing I'll do is run the small script. So I'm just copying the script. I'm going to my terminal here. Let's open a new one. I run the script. And what the script is doing is it's installing an agent. The agent is actually a container. So it's just a pod that is joining my cluster. And this pod is going to go inside and start to collect and feed some metadata of this application. You can see the agent here. Yeah, you see the agent is just happened to be installed. It's very small one, just use 100 millicore. What the agent does is it's looking around this cluster. It's not inside the app. It's looking at, hey, how many nodes do I have? What kind of node do they, what kind of node, how many CPUs, how much memory, how utilized they are, how many pods do I have, how many CPU and memory these pods or these containers use, how many do I have per node? It's all of this statistical analysis that is going to feed an AI engine. And the AI engine is doing what I said earlier, which means it's going to tell me, hey, this is how much you spend today on the 6 machine, this is how much you should spend instead, and the difference being your cost savings. So let's see, this button just appeared, it means the report is ready. So let's click on it, and yeah, here it goes. It's actually, let me turn this off for a second, so I'll explain to you what it is. Very interesting. So it says, yep, you can save 60% of your cost. Let's look why. So as I knew, right, in my current cluster configuration, I have 6 machines. These were the 6 machines that were here. So I have 6 machines. They are all M5 large, so it's a 2-core, 8 gig of RAM. So far, so good. Because I have 6 of them, it cost me $420. And in the Kubernetes world, this 6 machine means I have 12 CPUs and 48 gig of RAM. So that's effectively the size of my cluster, the size of the cluster on which the application is running. The engine says something very interesting. It says, well, you don't need these 6 machines. First, you just need 3 of them. And here's why. The engine says, look, you really only need, you already need 6 CPUs and 12 gig of RAM. Effectively, you're over provisioned twice on this cluster. It's a little bit less than the average. It's huge, it's still a huge number. And on memory, you're over provisioned 4 times. I mean, this is how massively over provisioned memory is for this app. So what the AI says and suggests is also, hey, instead of using 3 times this M5 machine, why don't you change the family and use this new 6A family. So let me tell you what this means. C means it's compute optimized, meaning it has less memory per core. So it's only 2 CPU and 4 gig of RAM, which is great because I am massively over provisioned in memory anyway. So yeah, it's a great thing to use a C class instead of an M class, which have more memory per core. So I like this answer. The other thing it says is a little bit more subtle. It says, look, why don't you use an A family? A in the AWS world means AMD. And so one of the secret is, or the secret of the cloud is some machine costs actually a little bit less depending on the processor they have for the exact same processing capacity. And on Amazon, and Google and Azure are fairly similar, on Amazon, an AMD processor is a little bit faster than Intel, but really it's like 1 or 2% more, but it costs about 5% less than the Intel processor. How would you know, right? There are hundreds of these machines on Amazon. How would you know that A means AMD and AMD is cheaper for the same amount of compute as the Intel equivalent? It's very hard to decide this. It's very hard to find out. You'd have to do benchmarking while we train an engine to precisely do that. So in my case, it's great because the engine knows that the A class or the A family, is cheaper than Intel, have a little bit more performance, let's say almost the same performance. Therefore, instead of having 3 M5 for 6 CPUs, I'm going to have 3 C6A because they are a little bit cheaper. And when you look at the cost reduction, you notice that I went from 12 CPU to 6 CPU, but my savings is more than 50%. So I reduced my size by 50%. My saving is higher than that because of the AMD processor. So that's why it says 60% savings instead of 50. The other thing that the engine says is you have some containers that are actually friendly to Spot Instance. And we make this an option as we always welcome the discussion and welcome the customers or the users to discuss that. Here, the engine says, look, there is a bunch of these containers. So remember, the containers were the green rectangles here. So it's a bunch of these containers that have a high replica, and most of them are not using storage. Therefore, they are friendly to use a Spot Instance. A Spot Instance is a highly discounted instance on Amazon. It costs about 70% less than a regular on-demand machine. The problem with the Spot Instance is they are unstable. Amazon may need to get the machine back, and they will actually give you only a 2-minute warning that they need the machine back. So only a certain type of containers are friendly to this because they know, or they almost are designed to handle this interrupt very well, where the node may disappear, and in this case, I need to replace it by another one, and I have 2 minutes to do this without creating too much stress for my application. So all these nodes here, all these containers, so this workload, these pods, are compatible. That's what the engine said. They are compatible indeed to use a Spot Instance. And that will give me another 15% savings. This is why I am at 75.7. And you see here the optimized cluster is now suggesting, yeah, you can use 2 of these 3 machines could use a C4 large Spot Instance, C4 and not C6, because right now there is availability on this region for Amazon for C4. Our engine is aware of availability in the region, so that's why it selects a C4 instance. And then this is just because I said, yes, I can use Spot Instance here. If I don't want, it doesn't use. If I want, it does. What you see on screen is a recommendation engine. It is something that analyzes the cluster, the utilization, the requirement of compute resources, and once it analyzes, it turns around and designs the best structure for the cluster. But what I'm going to do now is I'm going to get there. I'm going to get optimized. I'm going to do it without using Spot Instance so you guys can see the easy motion between left and right. And to do this, I just need to click on Start Saving Now. I'm going to do it now because it takes about a minute to run. So let's copy this script, go to my terminal and run it. And I'm going to explain to you guys what this does. So essentially, until now, I was just a read-only, right? I install an agent. The agent is living now as a container in my cluster, collects some information. This information goes to our mothership, our AI engine that is crunching the numbers and providing the report that you are seeing on screen. What I'm doing now is I'm asking the engine to optimize for me, and that's where the automation comes in. This is where the 10x improvement is starting to show. I am going to reduce my cost of my cluster, and I'm going to do it very, very fast in a few minutes. To do this, I need to effectively authorize our engine to start making changes. These changes are designed, these autoscalers, is rebalancing, are cost aware, so they're designed to reduce cost while not changing any of the performance. To do this, now let me show you the terminal. I went back into my terminal and I have created automatically a new user. This user have very restricted right. In particular, it can, you see here, access key and secret access key. This user can make changes, can add or delete a node. So it almost feels like it's another user, another team member that you got in your DevOps team, one that have the right to do certain things. The only thing it can do is optimize for cost. So it's a smart autoscaler that is going to shrink or expand your cluster, reduce the size to only what it needs. And from the moment it's optimized, it will keep this optimization with a cost-aware autoscaler or a smart autoscaler. Remember, it's still EKS, right? I haven't changed anything. I didn't even redeploy my app. Nothing has changed in my application. It's just that now I have a new member of my team. This member is going to manage my infrastructure on my behalf for this application. And this new member is cost aware. He's paranoid in making sure that the cost is optimized. So the user has been created, and you can tell the secret key and secret access key have been sent to the engine. I am ready to optimize, so I can start the setup. And I'm going to show you the fully automated version of it. Of course, there is a lot more things you can play with the UI, especially on the smart autoscaler. But what I'm going to do is I'm going to transform directly the cluster from something that is not that great into something that is much better. We call it rebalance or cluster rebalancing. I'm going to generate the plan. So I'm asking the engine, hey, please tell me what you can do very quick into reducing the cost of my app. The rebalancing has been established, and it says, look, for right now, you can simply change the 6 machine to these 3 machines. You spend $220 instead of spending $420. And how we do this is we are going to move away from this M5 and go into this target nodes. I'm not using Spot Instance because I didn't say yes, you can use Spot Instance. So it's going to be only on demand, but of course you can imagine that you can influence this engine in many, many ways. You can use Spot Instance, you can have headroom. Here by default, I have a 10% headroom, meaning I have a 10% space between what I need and what I provision. So it will take care of quick fluctuations. But I can decide to put 0 headroom. I can decide to put headroom only on the Spot Instance. So it's a cheap headroom. There's a lot of options like this. So I'm going to do it now. I click on rebalance and it is happening. So what's happening? Very simple. I am creating new nodes. So these are the 3 new machines that you've seen earlier. They were C5A in this case. They are being created. It takes about 2 minutes or 1 minute and 30 seconds for Amazon to create a node, the EC2 node, and to add that node into the cluster. So this is happening right now. Once the nodes are created, I'm going to give an order to EKS to drain the old nodes. And it's a draining process, meaning it's a process that if your application has a lot of replica, would not imply or inject any outage. It is going to slowly migrate all the containers from the old machines to the new ones. The old ones were not optimized, the new ones are optimized, and therefore I will reduce my cost by half. That's exactly what's happening. So you can see it here. Yep, you see it's already starting. So these are my 3 new machines. They just appeared. As soon as this becomes green, these new machines will have joined the cluster. So it's another few seconds and these 3 new machines will have joined the cluster. And then I'm going to drain, meaning I'm going to move these pods, these containers, and I will move them by asking EKS to do it, which means it's a draining process. It's designed for this kind of things. This is why we all love Kubernetes. I see it's happening right now. So I'm moving around, I'm deleting this, not deleting, sorry. I am moving these pods into the new places, and I am doing it very gracefully. If you go back to the console, you see it's happening right now. So I have created my 3 nodes. You've seen them on screen. I have drained the pods. Sorry, I have drained the nodes, which means I have moved the pods, the containers from the old things to the new things. And now I'm deleting the old things. So I'm deleting the old 6 machine that I don't need anymore, because now I have the new 3 machines. Yes, that's right. So that's what is happening behind the scene. It's a process that takes about 2 minutes. It's quite efficient in this case. If you want to see the result, there is here a very nice report that says, yep, you went from 6 M5 that costs $420 to 3 C5A. One is an X large that costs $224. And it took 2 minutes and 4 seconds. I mean, look at this. In 2 minutes and 4 seconds, I effectively reduced my cost by half. I did nothing, meaning I didn't configure anything. I didn't redeploy my application. I didn't change my CI/CD pipeline. I'm still using EKS, the one I know. The only difference is there is a new team member that has made this gracefully for me automatically behind the scene. That's exactly what you saw. And if you look at here, let me refresh the screen. Oh, this screen is not refreshed, so I'll show it to you in a second. But if you look, here's what I want to. If you look at here, you see I have a new savings report that shows a nice optimization. The reason why I can go even further to 168.67, it's simply because in my autoscaler, I asked the engine to plan for a 10% headroom, sorry, and the headroom you can see it here. Yeah, you see I have a 10% headroom here. Therefore, that's why it stopped at 224 instead of going to 167. But effectively, my cluster is optimized. I am spending $224. I was spending $420. I have made my cluster fully optimized. And from now on, with the smart autoscaler options I have, when I turn this on, from that moment, my autoscaler is now is cost aware. So it's a smart autoscaler that will continue to optimize my cluster as my cluster is going to start going to expand or shrink depending on the usage of my application. So that's what I wanted to show you. I showed you a very simple app that used 6 machines. I asked the engine, hey, tell me how I did. It showed me that I had a 75% option to reduce my cost, 60% if I don't want to use Spot Instance, 75% if I want. And then in 2 minutes, let's see again, in 2 minutes and 4 seconds, I showed you how I was able to move or optimize my cluster from something expensive to something ultra optimized that is only what I need, nothing less, but also nothing more, while I kept a headroom of 10% on that cluster by default. And that's something you can change at any time. So that's it. That's what I wanted to show you. Thank you very much for listening to me. One thing you should think of is this is a fully automated platform. You can go very deep into the details. You can create headrooms, use Spot Instance, don't use them, only for category, only for type of pod. There's a lot of options you can have, or you can select the fully automated version, which is the one I showed you. So thank you very much for listening to me. I look forward to hear back from you. You can send me emails. My email is laurent@cast.ai. I'm always super happy to hear from our users. You can actually also go to Cast AI. You can apply. It's completely free. So you can get your savings report anytime you want. You can even activate the exact same way as I did. Just go and sign up, and nothing prevents you to do that on your cluster. It will work for Amazon, for Google, and for Azure. Thank you very much.